Hello everyone, I'm Norman Wildberger from the University of New South Wales.
And I'm Daniel Mansfield, also from the University of New South Wales. We've come now to talking about one of our favourite tablets from the ancient world, Plimpton 322. And we have a fairly dramatic new interpretation of what this tablet actually is.
Yeah, so in this video we want to reposition what we think the tablet really is all about. It's really quite a dramatic, divergence from the standard story that's out there now.
Many people have had a go at trying to say what Plimpton 322 is really about, and we're going to say that it's actually trigonometry,
Yes.
but a different kind of trigonometry, and that's really the fundamental piece of the puzzle that's been missing from previous interpretations. This is a ratio-based trigonometric table.
Exactly. So let's have a look at what actually we are talking about. So the tablet is actually not too big. It's this is roughly its actual size, and it's known to be dated pretty close to the time of 1800 BC, which is during the reign of Hammurabi, which was very famous for his code. And I think we are pretty well confident that it's from a particular city in southern Iraq, which was called Larsa, an ancient city. And it looks like this. It has some headings. It's a little bit broken on the top left there, and it's pretty clear that there's a break on the left-hand side. There's a bit of damage here, but otherwise the entries are pretty readable. And there's 4 columns of sexagesimal numbers, with the last column very simple. That's just a row number going from 1 to 15.
So it's surprisingly small, but very detailed. It's extremely neat, and someone has come to a great deal of trouble to make a very careful copy of some actually very complicated information in this table.
We are going to be showing you the actual entries, and you will see that these numbers are actually quite significant. We're talking about base 60 numbers, and there's some of them, especially in this first column, are quite significant. So yes, our main claim is that this actually needs to be rethought, and basically we have to rethink a lot of things as a consequence of this, because this repositions not just this tablet, but it also repositions our understanding of trigonometry, and also gives us a new vantage point to think about trigonometric and geometrical things.
Yeah, it's a vantage point that we would never have come up with ourselves. It's from this completely different culture. It's very difficult for us to just drop thousands of years of mathematical understanding and say, let's look at it from a different, fresh way. And fortunately, we have this insight from an ancient culture, and we can learn of this new way of thinking about triangles from them.
Yeah. Okay, so let's have a look at Plimpton 322. So this is what it looks like. We have some headings up here, and there's damage to this first heading, so a fair amount of work has gone into trying to understand what it means. It's a little bit subtle. But these headings are pretty clear. And then here are the 4 columns of sexagesimal numbers. The last one is very simple. That's obviously a number of just the row, so going from row 1 to row 15.
And in fact, each row does actually say row and then a row number, so it's quite clear at least what this column is all about. Yeah, I should also mention that these are the corrected, or what is usually agreed to be the corrected tablet. Some of these numbers have been squished. For example, these 2 got squished together, and others had been replaced. Maybe this was a 901 and they meant to write 801. So there's some errors in here which we've corrected with what is usually agreed to be the correct corrections.
Yep. So let's have a look at perhaps the headings first to give us an orientation. So this first most complicated column, the heading is also complicated. It says something like this: square of the diagonal, subtract 1 for the square of the width. Okay, so there's something here that's to be noted, that all of these numbers appear to start with a 1. But in fact, the tablet, as we've mentioned, has been broken on the left-hand side, and it turns out that the break actually exactly aligns with these 1s, and probably the 1s actually contributed to the break. So there has been historically a bit of debate as to whether there are actually 1s here or not. But the heading itself is telling us that, well, whether there are 1s here or not, there's a close connection between the number that you have with a 1 here and the number that you have when you subtract the 1.
Yeah, it's difficult because, as Norman mentioned, this is where the break is, and the meaningful part of the tablet, the index and some other information, would have been out over here. So unfortunately that is missing, and it's really up to us to piece together what this was about. the most interesting part, I think, from this column is, well, there's so many interesting parts. One of them is the sheer size of these numbers. These are enormous. I mean, this one has 9 sexagesimal digits in it. What else is interesting about this?
And these are actually sort of like decimal numbers. I mean, the natural interpretation of this is 1 point something. So it's a number between that we would think of as between 1 and 2. So we are going into quite a lot of decimal depth. Like we're talking about very small change, whether that's a 40 or 30. And so it's quite remarkable that they were so concerned with such precision for some reason.
The other thing which really comes from the heading is that this has got something to do with rectangles or triangles and their relationship about their diagonals and bases. And it really took some time for people to figure out that these are actually squared numbers relating to a triangle or rectangle. In fact, these numbers here are, if you like, the squared ratio of the diagonal side divided by the long side. Or if you subtract 1, this column serves a dual purpose and gives you the ratio, squared ratio rather, of the short side divided by the long side. So really these are squared ratios. More importantly, they're exact squared ratios. There are no approximations in these numbers. These are all exact.
Yep.
And one of the things that Neugebauer noticed in 1945 when this tablet was first published was that this is not just any random sequence of exact square numbers. They actually describe something rather special.
That's right. So we'll see that there's a geometrical interpretation to these numbers, as the heading naturally suggests. I mean, we're talking about diagonals and widths, both here and in here. So it certainly suggests a triangle or perhaps a rectangle. And if we look at it from that point of view, then it will see that it's natural that this sort of is talking about a progression of inclinations that corresponds, what we might say, to a progression of angles. And that was noticed by Neugebauer and Sachs.
We also should mention these columns. The heading here is the ipsi of the width and ipsi of the diagonal. And the word ipsi would mean something like the result of some operation, perhaps a square root or some other kind of operation. We notice that there's not a clean pattern with these numbers. These ones seem to be descending nicely. Here they jump around from 1/1641 to 45 to 2759. It's much more haphazard what actually happens with these numbers.
But of course, the real thing that put this on the map is the fact that these numbers here, this number here and this number here, are 2 of 3 of a Pythagorean, what we call a Pythagorean triple. We'll see that, for example, in row 4, so this number here, if you converted that to a regular decimal number in our sense, that would be an integer, and that would also be an integer. And then if you square this number and you square this number, you see that this number squared plus some other number squared equals this number squared. So we have a Pythagorean triple at least 1,000 years before Pythagoras was around.
This is a very unusual thing to observe on a tablet. Pythagorean triples are quite rare beasts. So the fact that these are Pythagorean triples should really stand out on this tablet, and in fact it does really stand out in this tablet.
Of course, students these days, we know about the 3-4-5 triangle and the 5-12-13 triangle and some small ones like that. But it's pretty clear that these are significant Pythagorean triples, and why these ones and not other ones. That's very interesting. And how did they come up with these things? All kinds of interesting questions. So the trigonometry that we learn in schools is very firmly established with millennia of history and long usage. And it's a little bit hard for us to reorient ourselves sometimes to think about a different way of thinking. But we want to suggest to you now how the thinking that the Babylonians had is really quite different from our modern understanding of trigonometry. So our modern trigonometry really is based on the notion of an angle, which comes from astronomy, and it has had intimate links with astronomy for a long time. And so students learn that when we're studying trigonometry, the angle as part of a circle is measured perhaps by an arc length or perhaps by an area, is sort of an intrinsic part of measuring right triangles. Although we are interested in right triangles, we actually use these circular measurements to kind of encode or organize our understanding. So this will be a very familiar kind of story where we have a circle of radius 1, say, and then we have a typical triangle like this with an angle of theta, and then that's a cos theta, and that's a sine theta. And implicit in here is this idea that the shape of a triangle, a shape of a right triangle, can be sort of normalized so that its hypotenuse, or the diagonal, is 1. And then they all fit in this kind of pattern here. It'd be a pattern of increasing angles from about 45 to about 62. It's actually pretty well the exact range that we find in Plimpton.
But the Babylonians weren't concerned with angles or these ratios, sine and cos. And in fact, it's really difficult to actually use any of our understanding about triangles in this setup and apply it to the Babylonian sense, because they just didn't think that way. You can't orient a triangle according to an angle and then talk about an adjacent or opposite side. It doesn't work in this framework. Instead, they talked about rectangles with a short side and a long side and the diagonal of that object. There are also important ratios in this setup, but they're not the ratios that you see here. And that's really why this tablet has remained mysterious for over 70 years, because mathematicians come along and say, oh, it's clearly trigonometry. And yet they haven't bothered to clearly frame what kind of trigonometry it is. Of course, it's not about sine and cosine, and that's exactly what the historians have been saying all these years. You can't just say it's sine and cosine. That doesn't make any sense. So what we see in Plimpton is a different range of triangles with a different setup. Instead of having a hypotenuse of length 1, the rectangles have a long side of 1. They're normalized differently. Important ratios are then the ratio of this side to this side, the short side to the long side, and the ratio of the diagonal to the long side. And of course, the ratio of short side to long side is a very important quantity in both Egyptian and Babylonian culture. The Babylonians would call it the ukullu. And on Plimpton, we see the ukullu ranging from 5930 all the way down to 3720.
And these are, in fact, the exact values that correspond to the triangles in Plimpton. So this is actually the ukullu that is found in row 1, and this is the ukullu that's found in row 15. And this one here is almost a 45, what we call a 45-90 triangle. It's that one there, represented by that diagonal there. And then as the this ukullu decreases, it means that that length is decreasing, and there's actually 15 different steps. We've only shown 5 of them, but there's actually 15 different little steps going from this shape to this shape.
But the important things here are that it's a trig table, but not as we know it. It's a trig table with a different set of with a different framework, not in terms of angles, but in terms of ratios. And the second piece of the puzzle is they like to do it exactly. So these aren't just any old ratios, these are exact ratios.
Yeah.
So to distinguish the Babylonian trigonometry from the more familiar angle-based trigonometry, we've decided to call this Babylonian exact sexagesimal trigonometry. And we've hidden a subliminal message in here and abbreviated this to BEST. It's a very good way of doing trigonometry. Here we have an example of the kind of trigonometry they would study, and this is taken from row 4. The key things to notice are everything is exact and it's ratio based. So there's no angles anywhere in the setup, there's no implicit circle, it's part of a rectangle.
So the 3 ingredients are the B, the L, and the D. So the B is the short side, L is the long side, and D is the diagonal. Okay, and here the numbers are B equals 12,709, so that's in our system, taking their sexagesimal values and just converting them to our system. L is 13,500, and the diagonal is 18,541. So that is a Pythagorean triple, a not very obvious one.
It's kind of surprising when you encounter this Pythagorean triple. It's not something you'd expect to see.
It has another important property that we should point out. That's this L here. The L plays an important role. That's the long side. So when we showed you the normalized triangles on the previous slide, we were talking about a normalized length of 1. So this is a regular number in the Babylonian system. That means its factors are 2, 3, and 5. That means that the Babylonians could divide by this number. They could divide by this number exactly in their sort of sexagesimal system without resorting to fractions as we do. And so that allows them to think or rethink this triangle in terms of a corresponding normalized triangle, and then well, we'd divide everything by the L, and then certain ratios would come up.
And if you're studying a triangle, you want to know about these ratios so you can determine what the other ratios are. So in our decimal system, if we take these values of B and L and we divide them, we end up with 0.9414 and so on. This is an approximate decimal number. But in the Babylonian sexagesimal system, as Norman said, this is a regular number, and they can compute B divided by L exactly as 5629.4. And similarly, they can compute D over L exactly as 122.24.16. Now, we like to study trigonometric ratios such as sine theta and cos theta, and these things are always approximate. The Babylonians had different ratios, which is the first thing to get, or which is one thing to get your head around. The other thing to get your head around is their ratios 100% exact.
Exact in their sexagesimal system. So it's important that they're working in a sexagesimal system. They have more flexibility. They have more ability to make such exact calculations because they're working in base 60. Our base 10 would be very hard for us to do this, to demonstrate the same kind of thing.
But they seem to have very different priorities as well. We would want to frame things in this astronomical sense and have the notion of angle and regular intervals of angle, or equally spaced intervals for angles. They seem to emphasize rather the precision of this system because it's easier to work with numbers which are easier to divide by numbers that are regular.
And when we discuss the table in more detail in coming videos, we're going to see that these ratios actually end up figuring quite prominently in the story as well. So the history of trigonometry is intimately connected with the story of astronomy, of course, because the revolution of the Earth on its axis means that there's a uniform motion that way, and you want to understand where stars are, it means you have to consider the uniform angular motion. And so that's really been part of the story going back to around 700 BC, where the Babylonians also, but much later Babylonians, introduced angles, really for the first time that's been recorded. Their astronomy really developed further in the Seleucid period, sort of the Greek period, and then we have Hipparchus's table of chords around 100 BC, which is really the first official trigonometric table in the standard story of trigonometry. That's our first record of trigonometric data. But of course, since then, there have been many, many people who have worked very hard on trigonometric tables, and they have been very important for all kinds of practical reasons. And we can mention a few of the highlights. Ptolemy, around 200 AD, important Greek astronomer, of course. Aryabhata, an influential Indian mathematician and astronomer. Al-Biruni, an Arab astronomer. Madhava, a later Indian mathematician. So a lot of these people and many others contributed to ever-expanding understanding of angles and spherical triangles and laws of cosines and sines and so on. This whole paraphernalia that we have now of modern trigonometry.
And Rheticus comes along and he creates this enormous kind of extremely detailed trigonometric table spanning thousands of pages. And Rheticus is kind of an interesting example because he was really concerned about the errors in these calculations, and he was searching for some kind of solution to the problem of these approximations and the error in the approximations creeping up and corrupting his calculations. So I think Rheticus would have been very interested to know about Plimpton and its exact form of trigonometry.
Absolutely. And I'd like to point out, this is a very nice book by Glenn van Brummelen called The Mathematics of the Heavens and the Earth. And it's a history of trigonometry, so if you want to learn more about this kind of information, it's a good source.
And we really want to position the history of trigonometry slightly differently and start it a little bit earlier in the Babylonian period, because Plimpton 322 is a trigonometric table, but of a different kind. So if you like, we could rename this to be the history of angular trigonometry. The study of triangles actually goes back much further.
Yeah, so I think it's really interesting that we can now enlarge trigonometry by 1,000 years. We're talking about 1,000 years before this, and it's remarkable that it's not just the same kind of trigonometry but just done earlier. It's actually a quite different trigonometry going off in a quite different direction, and all the subsequent development is really on this sort of secondary path that's then grown and grown and grown. But this original path somehow just stopped, and now we're just discovering it again.
So it's nice to think that there's something we'd forgotten about up in the prehistory of trigonometry that we could now look at again and maybe develop and see what advantages it has. Yeah.